Hello, this is Christine Perret. Welcome to today's Interoperability and Standards webinar. I'm the leader of the Area Interoperability and Standards program, and I'm very pleased to have as my guest today Dan McPeters from Newport News and Marius Preda from Institut Télécom Paris. Min is in there somewhere, but he'll introduce himself momentarily. Welcome again. You are, it's June 17th. This webinar is being recorded and will be available as an archive from the Area YouTube channel as soon as possible. Today's webinar is going to have the following agenda. I'll be speaking for a few minutes about the area and our program to promote interoperability. And then we'll have our speakers talking about the activities pertaining to point cloud and point cloud compression. And then if you have any questions, you can put those into the question module of your GoToWebinar control panel. And at the end of this webinar, I'll be taking some of your questions and having a moderated discussion with our experts. So with that, I'd like to remind you a little bit about the area's mission. The area is the AR for Enterprise Alliance promotes adoption and accelerates the adoption of enterprise augmented reality. And we have three parts to the ecosystem that concerns us. At the top of this pyramid, I like to say that that's where the large enterprise customer segment is putting augmented reality to use for improving performance, productivity, reducing risk, and increasing safety. Supporting the large enterprises are the providers of technologies in forms of raw technologies, services, software and hardware products, and in partnership with them, the non-commercial entities such as universities, research institutes, and a variety of different agencies that are doing basic and applied research to advance this, this new ecosystem. So the area is concerned with those three segments and making thought leadership content, providing new opportunities for collaboration between them. We've found that some customers have a challenge when they're seeking to integrate their components into one solution or with their existing IT, and so we established the Interoperability and Standards program. In a way, it emerges naturally from this area schema of customer needs, because as you start from the top and go down, you see that there's this hierarchy of needs, and when the companies begin to identify the use cases, what they discover is there's dozens, perhaps hundreds of use cases within these companies. So what they need is a way to be able to leverage the investments they make for one use case across multiple or many use cases, many locations, and different environments. And so what that generates is sometimes a need to build, operate, manage a solution that's composed of multiple providers. You might have multiple different kinds of displays, different authoring tools, different software for managing experiences, and the customers and the systems integrators need to be able to knit together complete solutions with the lowest cost possible. And then there's also this need to combine augmented reality technologies with existing in IT management for data and operational purposes. So that's your existing security systems, your directory systems, network management, and all these are related to how AR can be delivered to the workplace and into the employee just in time and in context. And so in both of these directions, to the right and to the left, standards and interoperability are important. And that's why we created this program to help companies in all parts of the ecosystem understand the benefits and how they can begin to develop this interoperability. And then also in parallel to advance new standards or extensions of existing standards that can support interoperability for AR. And a lot of these technologies are not developed solely for or expressly for augmented reality, but can be very, very valuable when adopted in the right places by the right companies. So we have a set of policies and procedures, and what we're helping to do is identify the specific barriers, raise awareness to the solutions, and then we're doing that, as I said, through thought leadership content like this webinar, but also blogs and white papers, perhaps some best practice guides in the future. We like to support the standards development through identification of requirements, use cases that are popular for the end customer. When the standards get to a level of maturity that is suitable, we can also have our members review the draft specifications and conduct events that increase the communication and the understanding and deepens everybody's appreciation of interoperability and standards. And in the future, we hope to be able to do plug fests and other programs that help to test and build confidence in these specifications. So that's the end of our overview, or my introduction about the area and our interoperability and standards program. Now I'd like to transition to our guests today. Dan McPeters, he'll introduce himself momentarily, and then following Dan's remarks, he'll be followed by Marius Preda, as I said. All right, thank you. Dan, are you there?
Yes, I'm here. Can you hear me, Christine?
I hear you very well, thank you.
All right, thank you. My name is Dan McPeters, lead researcher for Dogfish Labs. Dogfish Labs is an advanced technologies applied research function for Newport News shipbuilding. For anyone who is not familiar with Newport News shipbuilding, we have about 23,000 employees, the largest employer in Virginia. We're located at a natural harbor at the James River and the Chesapeake Bay, which allows us to really build out very large marine vessels. 1886, we've been around since then, and constructing all sorts of marine vessels. In recent history, though, our focus is on naval nuclear propulsion vessels. Our natural harbor allows us to build and be the only builder of the Nimitz class and Ford class aircraft carriers, as well as our smaller vessels, our nuclear subfleet, Virginia class subs and fast attack submarines. It's funny how I reference these large submarines as our smaller vessels. What we do is very large, and it has always been very large. And what the vessels that we have built over the last 50 years need routine maintenance. They need refueling and complex overhaul. The Nimitz class of carriers is totally in this cycle of this overhaul. So very large ships that are very old, they were designed with vellum and hand-drawn drawings, which is an amazing thing to see in our vaults. Our newer ships are built with product model, but we have 50 years of vessels that do not have that luxury of having readily available 3D models. So when doing asset integrity and modernization on these older vessels, point clouds come into our bread and butter usage of point clouds is to gather digital information about the current state of these crafts and the compartments and the systems that are in them, so that we can use our modern digital technologies to facilitate design and engineering work. And that's largely what point clouds are used for. And in the shipyard is metrology, very refined measurements, and general assembly and design and engineering work. These are large ships. There's many compartments. There's thousands of compartments in a ship compartment. So our point clouds, in number and in size, get fairly ridiculous, I guess. Smaller compartments can be, 4 or 6 gig in size. Larger ones can be 40, 60, and even 100 gigs in size. This can cause obvious problems with storage. This can cause problems with transmission. The size of the point clouds can actually cause corruption at transmission with varied network connectivity issues, VPN secure connection issues. There's a whole host of problems that the sheer size of these scans can create. We're constantly having to upgrade our storage capacity into terabyte, beyond terabytes, and this really puts a stranglehold on our designers and our engineers' ability to have these readily available, to have these in the format or on the devices that they would like to have them on. And right now, there's a lot of different proprietary file formats of these that provide their own tools and specialties that you may or may not need, which provides another level of complexity and problems for our designers and engineers. There are ways to decimate these point clouds that are used, but that's often not what the engineers and designers want. They don't want to lose the data. They only want it to temporarily be smaller in order to transfer or to load or to store, and they want all that information to be readily available upon demand. A lot of times cost for licenses for specific hardwares, for specific proprietary file formats becomes an issue. Having to get individual licenses for individual features, for individual needs. So that opens up also a whole new problem in just the ease of working with point clouds. We don't want to strip away any of the data that, just because we don't need it now or because a certain discipline doesn't need it, doesn't mean that we won't need it 5 years or 25 years down the road when a ship comes in for an overhaul or for a modernization. We have internal ways of eliminating duplicates and trying to reduce file size and meshing point clouds together, but those also inherently lose data. So a standardization for us and for anyone in this type of industry is a win, not just to solve our current problems, but I think also there's use cases that we're not utilizing right now because of the problems that we're having where we are with just the sheer size of our point clouds. Now, other than our real bread and butter use case for point clouds, which I just described, is research that's going on right now with dynamic point clouds that can be used by machine learning to observe for recognition of maybe a workspace or a shop floor. The ships aren't the only thing that we do here. I think sometimes people say that we're a city that builds floating cities, and that's true. There's a 2 square mile area that's just full of shops and full of floors that are doing production, and we'd like to see what's going on those floors, not just in a security camera type way, not in a 2D way, but also in a real-time 3D understanding. This is important for going forward with Industry 4.0 capabilities. This is important for the use of fiducials and for markers and for robotic controls to someone who's not actually in the room for remote control. So there's a lot of things on the future side of the house that we're working with right now. But obviously, with our transformation into digital and to mobile, once again, the size of these files and is a roadblock towards even fast fail research at this point. But I believe that about covers just a real quick. I know I wanted to be careful of time here, but just a real quick look at how Newport News Shipbuilding is using point clouds today, and how we would like to use them in the future, given that they're a little bit more slimline and ready to use on mobile devices.
Perfect. Thank you very much, Dan. That was a great introduction to how this can be useful for your company and others going forward. Now I'd like to transfer the presenter to Marius. There we go. I see your screen. I see your slides, Marius.
Yeah. Hello, Christine, Dan,
and
everybody.
I hear your voice. Fantastic.
Good.
Thank you.
Good.
So how are you going to address all those problems, those wonderful requirements?
Yeah, let me let me give some hints about how they are addressed. I'm far to say that we have the solution of everything that was mentioned before by Dan, but let's say that we have the beginning of the solution. And since I'm talking about some standards, is even more than the beginning, because the standards is these standards are in preparation and will be published this year. But I will come later on that. So let me first put my slides here.
Perfect. Yep, you're in full screen mode. Thank you.
Great. Yeah, few words about myself. I'm Marius Preda. I'm with Institut Mines Telecom in France, and I'm also the chairperson of the 3D graphics group in MPEG. As you all know, MPEG is doing mainly multimedia compression, and point cloud is yet another multimedia representation. So at least this is my claim here today. But before talking about what a point cloud is, how compression can be done, and how it is addressed in MPEG, I will spend few slides in continuing this context that was introduced by Dan. Yeah, he mentioned more about a particular application. I would like to extend and first try to answer to the question, why is so hot topic today, this point cloud representation? So my point here is that we are with point cloud at the border of two worlds that are quite well known, with a lot of technology developed in the last 20-30 years. So on one side, we have what is the visual capture, and on the other side, what is called visual synthesis. And I will try to give some explanation, and you will all recognize what I'm talking about. So on the visual capture side, we start from capturing with one single camera, and then we add another camera and made the stereoscopy. This is quite old. Or a camera capturing the color plus the depth, and we have color plus depth. And then we start year after year to move, and we expand the dimensions. So starting with HD, full HD, 4K, 8K, and so on and so on. So the resolution is going higher. Then the color depth is also going higher, from low dynamic range to high dynamic range. But what is happening in the last few years is that we are also going towards what is a multi-camera system. So we are going in, let's put it directly as 3D content. So it can come in different configuration, trying to capture the scene or trying to capture an object within a scene. So we have different kind of rigs of cameras that are providing this immersive 3D representation of the real world. On the other side, in computer graphics mainly, we have visual synthesis. This is also quite old right now, but step by step, improving these technologies, we are able today to create natural looking content. Of course, it's still a mathematical representation. So we have all these primitives, geometric primitives, attributes, materials, lighting conditions, and so on, such as we are able today to reproduce to synthesize a content that is looking very natural. So when we want to put all this on the same slide, there is a clear border, at least there was a clear border in terms of expertise. These two worlds were quite separate. We had capturing people or visual capturing people and all the technologies, and then on the other side, computer graphics community. There were not so many exchanges between these communities. Of course, on each side, we have advantages and disadvantages. For the visual capture, it's relatively easy to produce. As soon as you have the material, you just capture and you obtain high quality content in a easy manner, let's say. And on the other side, we have the interactivity and immersion because it is a model. So it is possible by instantiating that model to create any kind of viewing angle, and and this is done in real time. So trying to put them together to have something that is doing both high quality, relatively easy to produce, and obtaining this interactivity and immersion, our claim here is that at these borders there is a representation. There are several things at that border, but there is one unique thing, which is the representation data, the representation format, and that representation format is the point cloud. So it means what? It means we have tools that are able to capture point clouds, and because it is a 3D representation form, we have the advantages of immersive and interaction like we have with any kind of 3D object in a 3D scene. Okay, so simply saying what the point cloud is, a set of points. So instead of having pixels in the 2D domain, we have points. There are some differences. These points are not ordered. Like in an image, we have neighbors, relatively easy to index. In 3D, there is no particular relation between them. So of course, we still have a distance-based relations, but it's not as easy as in 2D plane. And each point here is defined by a coordinate in 3D space, X, Y, Z, and by attributes that can be attached to these coordinates, like the color, reflectance, transparency, or any other attribute depending on the application. So in terms of representation, is not big deal, let's say. Some examples here, and this helps me to introduce also the applications. Dan already mentioned some of them, but there are also others. Like here is a point cloud content. You see it as a video because you cannot see it differently, but it's a pure 3D point cloud content that was captured by a multi-camera system. And yeah, here another one, just to show you that there are different views that can be rendered in the same time. So we are talking about 3D objects. Some examples that are also available on the web. You saw probably this basketball player that is a composition between 3D objects represented as point clouds and 360 background videos. Or this example from Microsoft where we have football players that are 3D objects that can be visualized in AR. And for this particular example, a point cloud representing such an object is something that is relatively expensive to represent, like going from 1 to 3 gigabits per object if we have to have an honorable quality. Other examples, but same. So we are here. Here we have a person, which is a point cloud person, very realistic because it was captured by a multi-camera system, and another person. That the second one is a real one. They are dancing together, and of course that visualization can be only performed by this guy here because he has a HoloLens device. But we can imagine many other cases. Yeah, one particular case that is very important is about autonomous driving. So these kind of systems are already there. So it can be used for driving of cars, but also this is what is used in robotics to have the localization and the navigation of the robots. And the simplest manner to have this representation is, of course, the point cloud. But here again, we're talking about huge quantity of points. Introducing some numbers for this particular example, you saw there are several thousands, hundreds of thousands of points, and an easy computation is that for about 800,000 points, we are talking about 1 gigabits per second, if it's non-compressed, of course. So we clearly see that if we want one day to use these objects, they should be compressed. Otherwise, there is no point in trying to use them. Okay, now let's talk about some basic principles for and how the compression is handled. One of the problems with this representation is that it's very sparse occupancy of the 3D space, and when we have sparse representation, is more complex, more difficult to do compression. So if in 2D we have for each pixels 8 neighbors, in 3D we have 26, which is fine, but many of them are transparent, so they should not be transmitted, they should not be represented. So only few of them can be used for doing prediction. And this is because the majority of 3D objects are not representing the volumes. There is nothing inside that object, but only the surface of that object. So we need special constructs to try to find a way of organizing this 3D space into another space that is more compression friendly. More compression friendly, it means that we are able to do prediction. Okay, the literature is quite full of solutions for how this special construct should be considered. So the ones that are quite well known are OC3, where the space is divided in cubes that can be further on divided, and this division is based on the content of the cube. So if there is no information in that cube, we stop the division and we only continue the division of the cubes that have more than 1 point in such a manner that a tree can be constructed, and therefore instead of having a 3D representation, we have this hierarchical representation. That is the oak tree, and also another manner is the KD tree that tries to keep, while doing this subdivision, a uniform repartition between the cells. Okay, oak tree and KD tree were demonstrated to be very good constructions for static objects, static scenes, but it's quite difficult to extend these performances to the temporal behavior. And why is so is, imagine that we have an object. So these are the points in the object. We have an object that is represented by these 3 dark points here. If this point is jumping in this other part here, I don't know if you see my mouse, but I hope you see. It means that that a
Yes,
full...
we see it.
Okay, thank you, Christine. It means that a full branch will jump. So if a branch is jumping, then the prediction is lost. So there are some challenges in using OC3 and KD3 for dynamic content. Okay, this introduction being made for generic principle in compression. I can jump now to how MPEG considered the issue of point cloud compression. So we start the work in 2014 on PCC. The theoretical advancements were quite known at that moment, and then also the applications were quite well identified. So what we did in April 2017, we issue a call for proposal. This is a formal standardization step, and the call for proposal usually contains a very well-defined set of requirements. So we knew at that time precisely what are the application requirements and what are the performances that we were looking for in terms of technology performances. So at that moment, we divided the point cloud in 3 categories: static ones, dynamic, as the ones you saw before, and something that we called dynamic acquired point cloud, something that was illustrated in my presentation with this autonomous driving use case. Then we had some answers to this call for proposal, quite well answered by leading companies. I will present later some logos. Many of them were interested in what we called category 2, this dynamic content, but was also a quite important interest also for the other categories. And we end up with 2 solutions. One is called VPCC, video-based PCC, and the other one is geometry-based PCC. And I will introduce both of them and give some hints why how they are different and what each one is doing. So we had a first committee draft in October 2018, and both standards, VPCC and GPCC, are planned to become final standards, one in July, so it will be in our next MPEG meeting in beginning of July, and the other one, it will be in October, the GPCC. Okay, so let me give you the 2 main ideas that conduct the developments of the first one, video-based point cloud compression. And these ideas are coming from computer graphics. They are quite known. And the first one is to use what is commonly known as displacement mapping, but it is the opposite of displacement mapping. So what is done in computer graphics, we are using the pixel intensity to deform the geometry of an object. What we are doing now is exactly the opposite. We take the geometry and project on an image and then encode the pixel intensity. That is the first idea. And the second idea is the corresponding of the classical texture mapping, where the color or any attribute associated to a 3D vertex is encoded as a 2D texture. So in the case of VPCC, it is exactly the same. We are creating a texture mapping, and therefore all the attributes are encoded as videos. So what is the basic idea? If we have our object here, the point cloud, the first step, so we are now at the encoder side. The first step is to segment this point cloud in sub-point clouds in such a manner that each sub-point cloud can be projected on a 2D plane. So then what we keep is that plane, an index of that plane, the color of the point projected in the plane, and the distance with respect to the plane. So when you do that for the entire point cloud, you have what we call patches. So the point cloud is composed by different patches that are colored here with different colors. And each patch is projected on a 2D plane, and therefore for each patch we keep some 2D information. To make it simpler, and this is one of the design objective of VPCC, we only use the faces of a unitary cube, the 6 faces, and the 4 additional diagonal planes. This allows us also to have all the computation on the encoder side in integer domain. It means what? It means that this 3D representation, that is a point cloud, is now represented as a set of 2D patches represented in images, and therefore, if the point cloud is dynamic, in videos. So we have the color attributes encoded in this image below here, and the geometry that is encoded as an elevation with respect to the projection plane for each point of the point cloud. As you may observe, there are some points in these images that are not used. So an additional information should be sent, which is called an occupancy map, indicating just by 1 and 0 what are the points from the pixels from these images that are used, that should be used for reconstructing the point cloud. Okay, so this is what you have to keep in mind. A point cloud is projected in 2D planes, patches are created, and therefore the attributes of the point, which can be color, reflectance, or any other attribute, is encoded as a texture map, and the geometry is obtained by a displacement with respect to a projection plane. But still, if someone is applying directly this principle, it may happen that some of the points, the 3D points, will be projected exactly in the same point as another one. So it means that that pixels is occupied. You cannot encode 2 pixels in one single pixel. And in that case, what we did, we add an additional depth map that is encoding additional points. So you can have as many as these point depth maps are required to encode as many as points are projected in the exactly same 2D position. It doesn't happen so often, but it may happen. And finally, just to be sure that we can have the bijection, the bijectivity, then in the worst case scenario, we also have a particular patch that is called raw point cloud, raw data patch, that is taking the points that can never be well projected. So in this case, we have a perfect equal between this 3D representation and this 2D representation, and that particular patch is encoded here in the somewhere in the image. Okay, so yeah, I hope you see the videos. This is what is happening when we have a point cloud. You saw previously in my video showing you this lady walking was relatively smooth motion, but when we project that in patches and in 2D, these videos are not smooth at all. But still, there are videos. And since MPEG is very good in video coding, we may say that the problem is solved. At least we can apply any video coding technologies, and we can have quite good performances in compressing this point cloud, dynamic point cloud data. Still, since this is not a pure video, we may have strange behaviors. Like here, between frame 12 and frame 14, we have this frame 13 where this patch, the big patch, was indexed as another number, and therefore when the packetization was done, this patch jumped from the position here to a position here, which can create some challenges for the video decoder, because the video encoders are usually looking in the neighborhood of the data to find the motion vectors. So it means that if we are only considering patching and packing per frame, is not the best solution. Deep analysis of this, and I will go quite quickly. So we have this fluid motion, and then we have the patches that are obtained by projection and packing in a 2D canvas. And for the ones that knows how video encoding is working, we may say that this representation is not very friendly with respect to the video encoder. And when we go to do the analysis, we observe that there is a lot of intra-prediction. It means that intra-prediction is, in this case, less expensive than inter-prediction. And you all know that in general, inter-prediction should be less expensive than inter. Okay, and this is also visualized by showing the motion vectors. And when we have motion vectors of this amplitude, then for sure the content is not the best with respect to video encoding. So yeah, another movie here showing exactly the same behavior for this other object. So the point here is to say that traditional video coding technology cannot be directly used for encoding this type of content. So therefore, there are some things that we can do. Instead of having the patching per frame, we may have an analysis of different frames, or we may have different criteria in creating the patching and the packing, such as that the temporal behavior is more stationary. And when we look at the differences between the first method here with no global packing, with the difference with respect to the fourth one here, where a method called global Tetris packing was used, we may observe that this video is much more stationary than this one. Therefore, the classical traditional video coders can do better job here. What is good is that this is an encoder only issue. The standard is not specifying how the patches should be created and how the packing should be created. So it means that we may have a lot of competition in the market to obtain very nice point cloud encoders. Okay, so yeah, it's about competition, and there are different methods. I will not go in details, but as I mentioned, these are encoder only methods. We may use motion compensation. We may use, and here is some experiments show a gain up to 20%, or we may use also a skeleton segmentation of the point cloud when the point cloud is a human, and therefore we may have even bigger compression. So to give you some numbers, you remember we mentioned about 100,000 points. So these are just numbers that can be easy to keep in mind. So 100,000 points at 30 FPS in uncompressed domain will be about 360 megabits per second. And when we compress that, we have 1 megabit per second. So here the main message is this ratio of 360 to 1, while keeping good quality from point of view of perception. So for the two objects that you already saw, where we have here 7 megabits per second and 4.4 megabits per second with an encoder with a reference encoder. So it's not the most optimal, it's far from being the most optimal encoder, but it's the one that you may have it for free from ISO even today. Okay, but this was about the VPCC solution. And as I mentioned before, in MPEG we have two solutions, because we realized that for sparse point clouds, doing projection is not the best idea, because in that case you have a lot of holes in the image, and therefore that information is not useful. So in that case, we applied a method which is pure 3D based, geometry based method that is using Octree, and Here to give some other numbers, for 100,000 points at 10 FPS, we have something about 112 megabits per second in uncompressed domain, knowing that we have the geometry and the reflectance here. Here is something that is captured by LiDARs. So this solution is what it's doing, analyzing the 3D space, analyzing the OC3 and encoding the OC3 with the possibility of pruning the OC3 at a certain moment and replacing that OC3 with surface modeling. This is for the geometry. So we have on this side the encoder, on this other side the decoder. They are in mirror. So we have the geometry that is using the OC3, and then the attributes, colors or reflectance or any other attributes that are using two manners. One is RAT transform, is called RAT, and the other one is using a lifting scheme that is representing different LODs. And everything else is relatively common: quantization, arithmetic encoding, and so on. So the main elements, as I mentioned, the usage of OC3 for the geometry, and with the possibility of pruning the OC3 and transforming in a surface, and then for the attributes, this RAT and prediction, LODs, and lifting transform. So some numbers here. We are talking about there are many applications that requires lossless compression. For this case, as also mentioned by Dan before, especially in maintenance, industrial maintenance. So it's very important to know what are the performances of the lossless schema. By using GPCC with the current encoder, same is not an optimal one, but is the reference encoder provided by ISO. We are at 20 megabits per second for this kind of content. And of course, if lossy encoding is permitted, it goes down 16 in this case, but with very high precision. That is a matter of the application. Not all the applications have the same requirements in terms of in terms of precision. But what is important to keep in mind is that we can go from lossless or near lossless up to loss. Okay, so a few slides about mentioning what is next. I mentioned about the fact that point out is that the convergence of these two worlds, but many applications are still using meshes, which is a very common representation with a lot of advantages. And our goal now is to revisit the past and have mesh encoder that is same using extending this VPCC and encode the mesh also as videos. So I will not go in all the details because I don't have too much time, but the traditional mesh is something very common in 3D graphics, which is mainly handcrafted by using more authoring tools. We have a set of points that are ordered, connected with polygons, and an animated mesh here is consists of changes of X, Y, Z, but the connectivity remains the same. So this is quite classic, and for that one there are already solutions, even standard solution to represent that. But we are now more interested in what is called dynamic mesh, which is a mesh for which the connectivity is varying in time, because frame after frame this connectivity is recomputed. You don't know how when you capture this kind of content, you don't know how the points are representing from one frame to the other, but at each frame there is a triangulation and so on. So it may end up, and it always end up with different connectivity. So here the idea is to add on top of VPCC this connectivity that is defined per frame, and therefore to have the video codec solution, but on top of that adding this changing of connectivity. So this is something that is in exploration. I can probably talk about that in, let's say, 1 or 2 years from now. I will conclude my presentation with some information about where data is available for vPCC and GPCC actually. So there is a website called mpegpcc.org with a lot of material. Software is available, open source software is also available for at least for Android. We know that there will be also software, but probably not open source for other for iOS mainly. And then let me also conclude. So we are talking now about novel capturing systems that makes possible to create 3D content and therefore have realistic quality, realistic immersion. The point cloud is something at the border between visual capture and computer graphics. It is possible usually with a lot of data, especially for high quality content. Therefore, the compression is absolutely needed. And by applying state-of-the-art compression, we can have manageable bit rates. One advantage, and this is also one of the reasons why we have these 2 flavors of compressing point clouds, is reusing of the video coding. A lot of technology is available there. So the vPCC is leveraging this existing hardware and software for a rapid deployment, but GPCC has a lot of potential in the sense that the full 3D structure is used there for prediction. And as I mentioned at the end, this PCC by its projective-based solution is providing a solid framework, and many other type of content can use exactly the same principle. Yeah, one disclaimer that I use several pictures and videos that were made available by a lot of people, and I have to thank them here. And thank you for listening. I will just show this slide, which is also introducing the question time, but to give the contributors in MPEG PCC, and means that companies that are preparing products, solutions for deploying MPEG PCC, either in the vPCC form for many of them, but also some others are preparing solutions for GPCC. Okay, thank you. I think I can stop here and take some questions.
Perfect. Thank you, Marius. That was really, really good and very, very interesting. One of the questions, in fact, you answered on this slide. I don't know how you could present as well as read the questions and answer them. That's a talent. So, well, this is very, very valuable. These encoders and decoders, are they envisaged as being on CPUs, or are there going to be, do you think there's going to be optimized silicon that accelerates these computations?
Yeah. That
I
actually,
don't see NVIDIA on here. I don't see, you know, some GPUs. What is the role of GPUs?
yeah, there are several points here. One of the reasons of going with vPCC was to reuse the hardware acceleration for video decoder. All honorable equipment, starting from the phones, even coffee machines, almost have a video decoder hardware integrated. So the main design principle of vPCC was to reuse as much as possible the video decoders that are already there. Currently, any video coding solution can be used with vPCC. So on top of that, we add something that can be interpreted as a kind of metadata. That means are some data related to patches, to how the patches are packed, but they are so light that their decoding is relatively fast. So it means what? It means that a VPCC decoder is a set of 3 or more, depending on how many attributes, video decoders, as they are, no modification of that video decoders as they are in hardware, plus a very light, but really light parsing. And therefore, you take directly the output of that video codec, send it on the something that is called reconstruction. That reconstruction is outside of the scope of the standard. But that reconstruction can be done in GPU. So if you have the transfer from the video buffer after the decoding and the GPU, then by composing in the GPU, you have directly the point cloud reconstructed. Yeah, that was one of the key elements in the design of VPCC, to stay as close as possible to the hardware and reusing what exists in terms of dedicated video hardware for video decoding and GPU.
What about implementing for
the same
GPCC?
cannot, indeed, the same cannot be said for GPCC, because GPCC is using something new. So of course, companies can create video decoders, GPCC decoders hardware. But I think this will come much later. I think first of all, people will start to implement VPCC because it's fast and cheap to implement. And then people are starting to create applications, content. And if at a certain moment we need to go more in terms of compression, then there will be hardware implementation of GPCC.
Okay, very good. Good answer. Dan, I think there's a question for you. When you were talking about the uses and the challenges around the use of point clouds at Newport News, I don't recall you mentioning augmented reality. And of course, this is the Augmented Reality Enterprise Alliance. So are there use cases that you envisage or you've already started with point clouds for AR?
Yeah, hear me, Christine?
Yes, I hear you perfectly.
All right. Yeah, we are looking into point clouds with augmented reality and because of the difficulties, it is a little bit harder to do, but some of the places that we're doing ongoing research are in telepresence, like Marius had in his video, the avatar of the person who seems to be in the room with you. This is something that we're looking into and trying out, especially for live instructor telepresence. Also, not just the person being in the room with you, but the environment that a person on site may be in. If you could make that available in an AR, a mixed reality, or a virtual reality experience, that is also something we're looking in with telepresence and how that how point cloud can become the reality for the person who's not there. Also, comparative environments. Sometimes we want to see what a point cloud of how it is compares to how it is now when the point cloud was taken. So there's places where physical reality and point clouds can come together. And yes, we are currently ongoing research on that.
Great, thank you very much. So I'm afraid we're just about out of time. Someone has asked one short question. I hope maybe Marius, you could answer this quickly. Have you found a way to save a 3D mesh quickly For example, if a car is driving down the road and has this, the scanners on, and there was an accident, could that be instantaneously saved? Is that in scope for PCC?
Yeah, if the question was to save the mesh and not point cloud, I suppose. Actually, when you capture something, you cannot capture a mesh. You can produce a mesh by capturing images that then you transform them in point clouds, which is an operation that can be done fast. And then mesh that representation to have a simpler representation than the point cloud, because point cloud is, even if it's simpler in terms of mathematical representation, is something that is heavy in terms of number of points. So you may create that. Then it depends also what is the purpose, because if the purpose is to have precise measurements, I would recommend to keep the point cloud representation. If the purpose is to only have a visualization of what was happening, then creating a mesh may be something that people can. Why is important is the process of creating a mesh from point cloud. If you want to do it automatically, is not as precise as it should be.
There's loss there. Okay, that gentleman finishes our webinar today. Thank you very, very much for your insights. And we look forward to how this all evolves as the technologies improve and as more and more companies adopt it. So thank you, and until next time, stay safe.
Thank you, Christine.
Bye-bye.
Bye-bye.